Today we're going to look at inverse functions. And inverse functions are the things that you've actually been doing ever since you started doing algebra. You just probably haven't learned them under this particular name. So when you think about it, the opposite of multiplying by 2 is dividing by 2. The opposite of subtracting 7 is adding 7. We've been undoing arithmetic operations by applying opposite operations ever since Math 60. So for example, the opposite of x subtract 7 is going to be x plus 7. Looking at it algebraically, if we take f of g of x, substituting the g function into the f function, we get x plus 7 subtract 7 gets us back to x. G of f of x equals x subtract 7 plus 7 gets us back to x. So these functions are undoing each other. That's what we call an inverse function. The inputs of one are the outputs of the other, and vice versa. Looking at specific points on a graph, if you have a 5, negative 2 being a point on a graph of f of x, then on the inverse function, the graph of the inverse function, then it have to be the point negative 2, 5. And just a side note here, the notation's pretty clumsy here for the inverse function. We use f with an exponent of negative 1 of x to indicate inverse function, which would make you think that it would be 1 over f of x. Not true, it's just poor notation, but that's what we're stuck with. So, formal definition of an inverse function is if you take the composition of the two functions and the result is x, then those functions are inverses of each other. And do you remember what we talked about one-to-one functions in the horizontal line test back in Chapter 2? Or was it Chapter 1? Chapter 2. Only one-to-one functions will have inverses that are actually functions. Okay, so just a reminder with the inverse functions, the input of one's the output of the other, the output of one's the input of the other. If we put 5 into a function, the result is negative 2, and then we put negative 2 into that inverse function, it gets us back to the 5. So that's how we tell if we're looking at an inverse or not. That doesn't help us find the inverse function. How we find an inverse function, we've got a little rule here. First, you want to make sure you've got a one-to-one function. And we do that by taking a look at the graph, seeing if it passes a horizontal line test. Like the graph of x cubed passes both the vertical line test and the horizontal line test. So we know it's both a function and a one-to-one function. And then what we want to do then, replace f of x with y. F of x is just a fancy name for y anyway. And then the critical step here is change the x's into y's and the y's into x's. And then we can solve for y and replace that y with f inverse. Just rename it again as being the inverse function. So let's get to an example. So this one's a linear function. F of x is 1/3 x subtract 6. And first thing I'm going to do is just rename it, call f of x y. And then the critical step here, I'm going to change my y into x and my x into y, and now I'm going to solve for y. So I can clear fractions, subtract the 8, add the 18 to the other side, and I get the y by itself. And so this is my inverse function, 3x plus 18. Now on the calculator, if we compare the original function and the inverse function, you'll see an interesting graphical relationship between the two. So here's my original function, 1/3 x subtract 6, and then my inverse function, 3x plus 18. And then just for clarity, I graphed the line y equal x in here. And you can see if you fold the graph on the line y equal x, these are mirror images of each other. So that's a nice way to double check that you actually do have an inverse function. And then also notice that, say, the point negative 6, 0 corresponds to the point 0, negative 6. So between the inverse function and the original function, any one point xy will have a corresponding point yx. Okay, this one's a little more complicated, and it looks... Okay, get my page messed up there. So this one's a little messier. It is a one-to-one function. It's a little tough to tell. We'll talk more about graphs of rational functions later on. But we're going to take the function, we're going to swap the x's and y's. And what's making this one complicated is y's appearing in two different spots here. So again, I'm going to clear fractions with multiplying both sides by y. And I still have two terms with y on them. And getting both of the y terms on the same side, I can then factor out the y and then divide to get my inverse function. Let's do one more that's not quite as hard as that one was. Oh, actually, let me go off on a side note here. One thing about functions, there's an awful lot of perfectly nice functions that we use a lot that are not one-to-one functions, like y equal x squared. But one thing we can do is if we restrict the domain of a parabola to say just the values of x greater than or equal to 0, what we get is half of a parabola, and that is a one-to-one function. And just think about it a minute. What undoes x squared? The square root of x. So the square root of x is the inverse function for x squared, but only if we restrict the domain to x values greater than or equal to 0. Okay, so this one here, it comes to us with the restricted domain. So we've erased this side of the parabola, and we're only looking at this piece here. So again, if the domain restricted, we do have the one-to-one function. We can find the inverse. Um, I lied to you. This is the hard one. So what we're going to have to do this time is complete the square. So I'm going to kick the 2 to the other side, find my magic number. Half of -6 squared is 9. Add that to both sides. Factors. Then I can take the square root of both sides. I'm only going to take the positive square root. Again, because of that restricted domain, I'm only interested in the positives. And then add the 3 to get my inverse function. And then again, graphically comparing the two, we can see we've got that symmetry there with the line y equal x. Okay, this is the one that wasn't quite so bad. Probably should have done that first. So f of x is x plus 2 all squared. We've got the restricted domain, so we're only looking at half of the parabola. I've got it cut off at the vertex here. Change the x to y, the y to x. Square root both sides. Again, only want the positive square root because I only want half of the function. Subtract the 2, and there's my inverse function. And then graphically comparing the two, we can see we've got that symmetry. And then take a minute and look at the domains of these. The domain of the original function here, this half a parabola, the domain was -2 to infinity, how far left and right it goes, and the range was 0 to infinity, how far up and down it goes. For the inverse function, the domain is 0 to infinity, and the range is -2 to infinity. So what was the domain of the original function? It's the range of the inverse function, and what was the range of the original function is the domain of the original function. And that's always true with inverse functions.